All right.
Okay, how's everyone doing? How's prelim season? Yeah, rip, I know. The grind is real. But we have a fun night ahead of us. We're going to talk about relational databases. Without further ado, let's kick it off. Alright, so first, a recap on what we know right now and what we've gone over so far. So, beginning of it all, clients talk to servers. So we have a computer, and it's communicating with the server via requests and responses. So client sends requests, server does some stuff, and gives back a response with the data or indicating the success or failure of the request. So say when a request hits the server, the first thing that's going to happen is it's going to trigger the app.route decorator that we have. So this is indicating like the route path and the methods for the request. And so request comes in, app.route, then redirects to like get whatever data we're looking for, and then it's going to return a response back to the client. And that's like the high level, like what's going on with any request that's hitting the server. So going into more about like what getting data and what we did with the last assignment. So now we have servers are interacting with the database. So before that get data part of the request, we were just handling by manipulating a posts dictionary. But now in the last assignment, we made the transition to a database for an actual like better data store. And so servers communicate with the database via SQL queries. So for us, we're using SQLite to be able to write SQL queries with Python strings. And so this SQL query gets executed by the database. It goes to the table. It gets whatever data we're looking for or updates whatever data. And then the database will return the data that we're asking for. So then altogether, this is what it looks like. It's like a nice map. So client sends a request. Server will then make the SQL query to the database. The database will give back some data, and the server will then return the response appropriately back to the client. Are there any questions about this model and what we've been doing so far? Any clarifications needed? Coolio. All right, getting into it. Also, we made a single table database for the last assignment, so we just had a users table that we would update the balance for with transactions and sending money between our users. So a table is just a way to store information via rows and columns, where the rows represent an instance of a collection of the column fields, and each column has its own field with a specific type, and that type is enforced for all rows that have a field in that column. So we are able to query and manipulate the database with SQL, as mentioned before. So this is how pretty much every table works in a database. So now we're going to talk into relational databases where we want to have multiple tables. So we want to allow relationships between data. So what I mean by this is say like we have the posts and comments like we did for the first assignment. Like how do I keep track of which comments belong to which posts? A lot of students ran into issues like how do we want to model this data? Do we want to nest comments within the post dictionary? Some people had comments be either separate dictionary but had kept track of the keys between the two. But this general question of how do you want to keep track of what information is related to what information of a different type, that's what we're trying to solve. And then also for like users, like how do I want to keep track of users who are friends with each other? Questions like this we can solve with relational databases. So take this example of users and posts. So a user simply has its ID field for as every table does, and then a name, and then a post table has its own ID along with the text of the post and the author. So the first thing to notice is that these, the author key, if you look at this number 2, is referring to an ID in the user table. So that's how we're creating that relationship of this post with ID 1, welcome to my blog. Its author is represented in the user table. And the same is true, and this is what we call a foreign key. So a foreign key is just a field in one table that indicates an identifier for a row in another table. So that's how we connect information across different tables. So it also can go under a name called the secondary key, but also the key can refer to the same table or a different one. So say in the case of users and friends, a user is a friend with another user, so it belongs to the same table, so keys can refer to the same table. So also whenever we have a foreign key column, it indicates that we have a relationship going on. There's no need to store the key of another row in a table if you're not going to use it for any like linking of the data between them. Cool. So there are many, when we say relationship, there are 3 main types: one-to-one, one-to-many, and many-to-many, and we'll get into the gist of what each of these means. So one-to-one. So this just means, so like a single row in one table is related to one and only one row in another table, and vice versa. So this diagram on the top right shows that, like, imagine those blocks are a row, each within their own respective tables. They're only linked related to one item in the other table. So an example would be students and net IDs. This is like a one-to-one relationship where every student has a net ID and only one net ID, and a net ID can belong to one and only one person. So an example of what this looks like when we're talking about tables is, imagine we have a person and a profile, so we're like making a social network and we want to separate the two. So person would have its ID name, and then profile would have ID stat, like just say a status, and then a person ID. So notice that the person ID in the profile table corresponds with a unique person in the person table. So here 10 refers to 10, and then also 20 and 20. So they're going to be one and only one, and yeah. Any questions on one-to-one so far? Cool. So what does this look like when we actually write SQL to build these tables? So if we were to create these two tables, as we know right now, we need to create table person, define the ID, and define the name. And then for the profile table, the big thing to notice is the person ID. We're going to make it an integer just to keep all of our IDs of the same type so it's easier for us. But we're going to say unique. We want to say unique because this is like the nature of a one-to-one relationship where there can only be one person in the profile table. Each person ID is unique within that table. If we had two person ID values of the same value in the profile table, that would break that constraint. So that's why we're saying it's unique. And then the last line here says the foreign key person ID column references the ID field within the person table. So that's how we establish that relationship. And then this is what an example of how we would insert values into our database. So usually we'll just insert John into our person table, but then for profile, say the ID of John was 1, we want to insert into the profile the status and the person ID, just like any other columns for a table, and then we could say, oh, he's away and his ID is 1. Alright, so getting into one-to-many, the diagram shows kind of like 3 rows in one table being related to a single item in another table. So for a certain row in a table, it can be related to many rows in another table. But the reverse is one row in the second table can be related to one and only one row in the first table. So an example of this would be like posts and comments like your first assignment. So every post can have many comments. It's not limited to any certain number, but each comment refers to one and only one post. So we'll go through another table example here. Say we have a music streaming service. We want to have albums and songs. So album has its name, songs has also its name, and then major key, the album ID. So say we want to look at Igor, what are its songs in that album? So we can see in the song table, we look for the IDs of the same ID of the album table. So 105, you can see, has 2 here in this case, and then similarly for 444, also has 2. So for a single album in the album table, it can have multiple songs referencing that same ID. All right, and this is how we want to create this one-to-many relationship. So album ID name, and then a song, it's the same thing, but instead we're no longer asserting the album ID integer is unique, we're just saying it's not null. We're not asserting uniqueness because we want to have many songs being able to have the same album ID value within that column. And once again, we use the syntax foreign key album ID references the ID value within the album table. All right, the final relationship we're going to talk about, and here's another example of inserting, is, and you can retrieve an album song simply with something like this. So we want to select all the values from the song table where an album equals a particular ID value. So in this case, 105 was Igor from the album table. So this is how we get all the songs for an album. All right, next is many-to-many. So as the diagram suggests, a row can be related to one or many rows in another table. So I'm not going to read that algebra stuff, but just an example, like posts and hashtags. So anyone can make an Instagram post and hashtag it with as many hashtags as they want, and then each hashtag can have many posts relating to it as well. So there's that like whole networking web of like many-to-many. So an example of this with tables, we need to talk about implementation. So when approaching a many-to-many table design, there are three main concepts that we could work with, and two of them are actually not ideal. The third one, join table, we'll show last, is the best way to do it, but I want to show the two ways that people may intuitively feel is the best, but and show why it's not ideal. So the first one, columns to store a list of IDs. So say we have students in courses, like we're modeling CMS or something, and we want to store what courses a particular student is in. So that's what this courses column on the far right of the student table represents. So in this case, student 1 is taking 1110 and CS 1998. And as you can see, they relate to IDs within the course table. And then similarly for a course, say 1110, we want to know what students are taking 1110 right now. So you can look back and look at its list 1, 3, and then find those IDs in the student table. So this seems like a simple and easy way to go back and forth between looking at the related data between the two tables. But this isn't great because lists are not an easy data store to have in a column. There's some low-level reasons why this is difficult. Some database frameworks allow you to put array fields in as a column within a table, but typically runtime's not as good, and we can be more creative in how we're approaching a many-to-many relationship to make this faster and more efficient data-wise. The next approach we can try to do this is just have a column for every course that we want our students to take. So that way students could have many courses, and then the course would similarly have some columns, and it would be able to relate back and forth. But the big question with this design is what happens if a student wants to take a fifth class? Because we don't have a column for it. And if we wanted to allow students to take many classes, we'd have a lot of columns, a predefined amount always, but we would end up having a lot of null values in the columns, and we'd just be wasting a bunch of space. So this is a big crux with the storing a certain number of columns is you can't anticipate all the use cases, and if you try to anticipate a lot of them, you'll end up with a lot of null data, and that's not great. And then the third and final implementation is kind of going back to the idea of the lists that we had before. They're red because we don't like how they're being done, so we're going to remove them and do what's called a join table. So a join table, it's also called a bridge table. It serves as the intermediary to go back and forth between the two tables' related information. So say we want to look at student 1 and find the classes that they're taking. So we'd go to the join table and find every row that has a student ID of 1. We'd see it's related directly to a particular course ID. So in this case, 1110 and 1998. And so we traverse over this bridge table, this join table, to find the classes that the student is enrolled in. Similarly, if we want to find all the students taking 1110, we go to the join table and look for all the rows where this course ID is equal to 1110. So in that case, it's these 3 rows, and then we take those student IDs and look at the student table to get the student's information. Any questions about traversing across the join table to find related information here? All right, cool beans. Okay, so how does this look like? What does this look like in SQL? So we have our 2 tables for students and courses. They both have an ID, and then students have a net ID, say, and of course we'll have a title. Now, how do we create this join table? We want to do something like this. So it's basically 2 foreign keys. So we have a join will have its own unique ID, and then the course ID it's referring to, and a student ID it's pairing it with, and then the according foreign key references to tie those fields to the 2 tables that we're relating. So in this sense, it's almost like we're creating a 3rd table that has 2 one-to-many relationships, but in effect making a many-to-many relationship between our students and courses. All right, so now how do we want to query on this information? So a join query is an archetype of working with many-to-many relationships, and it's basically combining information from 2 tables in one query by looking through the related columns, just like we were going through earlier, but in actual code. So there are 4 main types of join queries: the inner, left, right, and outer join. We will be covering the inner join in this lecture just to show you a glimpse of it, but we actually won't be having you do any join queries in this course because we don't need it for the scope of our applications. But if you want to know, that's all the different types of join queries you can run. So starting with the inner join, you can imagine it like this Venn diagram here where we have two tables and we want to find the intersect of their information. So where we have columns lining up with each other. So let's combine the records that have matching values in both tables. An example of a join query is this. So we want to get like the course ID within the join table and a student's net ID. So seeing what course IDs have what students enrolled. We would look from the join table and we do an inner join on the students. And the condition we're looking for is where the join student ID column is equal to a particular student ID. So in table representation, that would look something like this. So we have our two tables. The left is the student table, and then the one on the right is our join table from earlier. So say we want to, we'll move and create our net ID column, being this student.net ID that we want to have in the end. And then we'll look through for each student and through all the students in the join table and find where the IDs match up. And then where they do, we'll copy the net ID and the student's information over. So then for each student, we see where the rows are matching, and then copy over the net IDs. And then now, because we only want to select the join's course ID and the student's net ID, we're going to get rid of the student ID column when we return our result. So table representation of what this query would return would be like this. All right, so the next thing we want to try is say like we don't want the actual like ID of the course, but we actually want to get related information that has that course ID. We do kind of a double inner join at the same time. So inner joining both the tables at once, and we do that with a query like this. So before the from was just the join table, but what we want to join from is going to be like a join itself with the course table. And then after we join it with the course table, we're going to join it again with the student table. And then the information we're looking for at the end is course title and student's net ID. So try to get all the students enrolled in all the courses. So here, starting with the courses table on the left and the join table on the right, we're going to go through the similar process. We're going to create like our title field that we're looking for, and we're going to go through each course, find all the instances where they match up, and then copy over the information that we want. Then because we only want to keep the course title, we're just going to ignore the course ID for now, and now we'll start doing our inner join with the student table. So the student table is now on the left, and our joined table of the, there's a lot of joins here, okay. This table on the right is the result of the join in the parentheses in the middle of that SQL expression. And now we're going to inner join it with the student table. So going through the same process, looking for where the student IDs match up, and then copy over the information. And then now, because we only want the course title and the student's net ID, we're going to get rid of everything else, and then this is what the query is going to return us. A list of all the titles of the courses along with all of the net ID pairings for our students and courses database. So now say we wanted to just look for students who were enrolled in 1110. What we'd add at the end of this query would just be a simple where title equals CS 1110. And that would give us back a list of all the students enrolled in 1110. Even though they're part of two separate tables, by doing these inner joins and combining the information from the two tables together and then filtering it afterwards, we're able to write like relatively complex queries, which is really cool. Is any questions about the inner join process, or like me to go through it again? Okie dokie. Alright, so this is like a Venn diagram representation of what the other three join queries look like. So left join, same example of students as table 1 and courses as table 2. A table 1 would include the intersection of those two, so it can be like an inner join, but it would also contain all of the students who aren't enrolled in any courses, which seems kind of sus, but it just allows, you wouldn't be, so in the initial query for the inner join, here, this on join.studentID equals student ID, a left join would allow us to have a no value for join.studentID, and it would still take that student's information and throw it in a return query. Oh, wow, a lot of animations. Well, you guys see it again. All right, cool. And then similarly for a right join, with students being table 1 and courses being table 2, if we did a right join of the two sets, we get the intersect plus all of the courses with no students in them. And then an outer join would return us all of the information together, but not caring if any of the data lines up. So it would give us a bunch of null values for courses that have no students and a bunch of null values for students that have no courses, but it would be okay. The reason I chose to show inner join is because that's the most useful one, in my opinion. And especially for our applications, you really care about finding where certain data equals each other, and you don't want a bunch of nulls everywhere if you're doing some data analysis or anything like that. Cool. All right. So we can do the demo now because I won't have a lot of time for that. But does anyone want me to go through any of the joins or talk about the relationships one more time, just refresh yourselves, or people happy to do the demo now? Yeah.
Can you just repeat right join?
Right join, yeah. Yeah, so the right join is kind of analogous to the left join in that it's going to get the intersection of the two tables where the key values are equal, and then it's also going to include it's going to include all the values in the second table we're joining with, where the IDs of the first table don't line up in any fashion. So it's going to give us the intersection plus a bunch of extra course data. And then for left join, it's going to give us the intersection plus a bunch of extra student data. And then the outer join will be the union of all that data. So, sweet. Okie dokie, let's see how we actually write this in code then. I'll pass it off to Alicia.
All right, it's demo time. So, from our code before, I'm going to keep running with our task demo that I've been kind of doing for the past few lectures. So today we're going to model a one-to-many relationship. So this is very similar to what we did before with the posts and comments. So we'll have tasks and subtasks. So you can imagine, say your task is do homework, but maybe you want to break it down into more tasks. So you'll say, instead of just do the entirety of my network's problem set, you want to do question 1, do question 2, do question 3, and maybe it's easier for you to track that. So we're going to want to create a different table called, needs to be bigger. Be enough? Oh, yeah, I can do that. Is that good?
I didn't change the projector.
Oh no.
The projector's kind of weak.
Why is it weak? Can I do another theme? Light mode, how do I do this? Preferences, settings. Oh, I saw color theme actually.
Speech.
Color theme? Oh, let's do light. Is that better? All right, I don't like light mode, but I'll do it for you guys. Yeah, so in this example, we're gonna wanna create tasks and subtasks. So the nice thing about one-to-many relationships is that when we create our new subtask table, we don't actually need to edit anything we have right now with our task table. That's because we're just going to refer to our original task in our new subtask table. So let's go ahead and create that. It's very similar to what we were doing before. We already have our connection, and then we're going to execute a SQL query where we're going to create our new table. And that looks like create table subtask. And what's in here? We have our ID again, that's going to be integer, and this is our primary key. We're going to have a description, again, text not null. We're going to have a Boolean done. And the new thing we're going to add to our subtask table, as Connor's explained before, is a foreign key. So we're going to want some sort of column that represents the task that the subtask belongs to. So we can just write it as task ID. And this is going to be an integer because our original, the task table ID is also an integer.
Give him more time to type.
Yeah. And how do we specify that this is a foreign key? We write it in here and we just say foreign key, and then we say which column we want to be the foreign key, which is our task ID. And what is this going to reference? We will call our table name here, which is task. And then we have a field in task, which is ID. So this ID here refers to task's ID and not like our subtask ID. Give you a little bit of time to write. And because we have a try statement, we're gonna want to make sure we catch any exceptions. All right, so I have a couple of methods here that I'm going to end up filling out just because it's like the basic methods that we want when we want to insert or get our subtasks. So the first one I'm going to do is get all subtasks. This is just kind of a sanity check so we know what is going on in our new subtask table. Generally, you probably wouldn't actually want to use this in your API because it's like, why would you want to view all subtasks? Like if it's not correlated with any of your actual tasks, that's a little bit not useful, but we'll do it for the love. So we're going to execute a new SQL query. It's going to be, we're just going to select everything from our table subtask. Then subtasks, we have a empty list. So that means when we iterate through our cursor, we can just append our subtask. And remember that we want to return this as a Python dictionary instead of whatever cursor object that SQLite uses. So we can just go ahead and grab this like ID, which is going to be row 0. We're going to have our description, which is row 1. And remember, this is in the order of how you define your columns. We have our done. And then row 2. And then finally, as a sanity check, we'll also return the task ID. You probably wouldn't want to do this in like an actual response, but again, we just want to make sure that everything is updating correctly. And I'm gonna cast this done to Boolean because it's actually saved as like 0 or 1 inside of SQLite. So when you actually return this, it'll say like 0 or 1, but if we cast it to Boolean, then it's fine. And then once we do that, we want to return our subtasks. So something important to note, you might be wondering, like, why is it necessary that we actually have to like declare that one of our columns is a foreign key? Because you can think of it as like effectively it's just a column of IDs, right? Like you didn't really need to specify foreign key. You could just have this part and be done with it. But the nice thing about databases, as we talked about earlier, is that we can create constraints on what sort of data you can put into your database. You don't want to just put whatever. So an example of why we would want to label a column as a foreign key is what if you want to add a subtask to a task that doesn't actually exist? So maybe if you create a new subtask and the client says, oh, I want this subtask to go to task 1, but you don't actually have a task 1. What if your task list is empty? Then if you try to create a new row in your subtask table, now you have a subtask that points to a task that doesn't exist, which is not what we want. So SQLite will take care of that for you. If you declare one of your columns as foreign key, it will return an error if you try to do that, which is nice. Because we always want to err on the side of don't put things in and let us know when constraints are broken versus just go ahead and put it in and then now you're going to regret it later when your client doesn't understand what's going on. Something about SQLite here though is that it doesn't actually enforce the foreign key by default, as in sometimes it will let you actually just go ahead and insert an ID that doesn't exist. So to do that, we actually have to manually specify that when we create our connection. So if you want to go back up to your initialization function here, I added a line, which is a SQL SQLite command, pragma. So this is like a foreign key flag when it like compiles. And this is just saying that, hey, I want to make it so that if you insert, a foreign key, make sure that it actually exists in the reference table. So make sure you have that, or you might get some anger. So what actually happens if you get that error where you try to insert a new foreign key? It will raise something called an integrity error, and we're going to be catching that later on. So you can use that to make sure that you're not doing something that's illegal. All right, so now we want to insert a new subtask. So you see here, not only do we give a description and done, we will also now give an ID, which is referring to the task ID. So this is our foreign key here. And this is pretty straightforward. We're going to create our cursor. And we're going to use this cursor to execute a SQL command. So insert into our subtask table. And then we want to insert the description, done, and now also our task ID. And then we want to specify the values, question mark, question mark, question mark. And we want to provide a tuple with our values that we pass in as a parameter. Sorry, this is very long. So it looks very similar to how we created a normal task. It's just now that we're also inserting our task ID. So once we execute that, remember that because we're like modifying the database or the tables, we need to save it, which we do by committing it. And then as before, when we create this new subtask, we're just going to go ahead and return the ID of the subtask we just created. So we can do that, cursor, last row ID, meaning the last row that we modified, take the ID of that. The last row we modified is, of course, the subtask that we just created. All right, so the last thing that we're going to want to implement for now is get the subtasks of a task. And this is kind of the most important useful function because given our task ID, let's see all of our subtasks for that one task instead of just looking at all the subtasks. So again, here we pass in an ID. This is referring to the task ID and not the subtask ID. So we're gonna want to create our cursor. And then we can use a conditional query to only select values where our task ID inside of our subtasks is equal to the ID that we're giving here. So we can just do that by selecting all columns from our subtask table where task ID, which is a column in subtask, is equal to question mark. And again, we want to give a tuple that only contains one thing, which is our task ID here. So yeah, this is going to, select everything from subtask where the task ID is equal to the given ID. And we want to get our subtasks here, so let's just initialize an empty list. And then again, for our rows in our cursor, we want to just do subtasks dot append, and then we want to create a dictionary. So that's ID row 0, description row 1, and then our done row 2, and then I'm just going to cast that to Boolean, so when we look at our response, it's going to say true or false instead of 1 or 0. Oh, semicolon. Did I forget semicolons here too? Oh my lord. It's hard being in Python land. All right. Did I forget one up here? No, I'm good. Oh, equal signs? Oh, it doesn't actually matter. It can be double or single. It's like the same. I think I might have used double earlier. Oh, okay, yeah, you can use either. It's fine. Here? Task. Oh, yeah, sorry.
Oopsies.
That should be task. That should just be ID. Thank you. Anyone? Yep. Oh, here. Yes. So this is just executing a SQLite command to say that, hey, let's actually enforce our foreign key constraint. And this is just setting it true.
Does it need a semicolon?
Nope.
No semicolon needed.
No semicolon needed. Cool. So once we have our subtasks, we can just go ahead and return them. So we have a couple of our database helper functions. How are we going to modify our app.py to support this and in terms of creating new routes? So I have some here if you want to quickly just jot them down. The routes are pretty straightforward. We have given a task with our task ID. We want to do something with the subtasks here. So you can see that for create subtask and get subtasks of task, we have this route because we only want to create a subtask for a specified task or get subtasks of a specified task. Down here, we also have a route that's just subtasks, and this is just getting all subtasks. And I'll actually go ahead and implement that first because that's kind of the most straightforward. So it's very similar to just get tasks, like what we did before. So we have our response with a success. Hopefully it's true. And then our data, we can call. So remember we have our DB database driver object that we created before, and we can call our get. Oh, is it here? Get all subtasks. db.get all subtasks. And this will return the list of objects as we needed. Then we can just do return json.dumps res, and then our status code is 200 because it's all good. And this, if you look at this right now, it's exactly the same as our get tasks, except calling different functions for our data. All right, so let's create a subtask. So we want to create a subtask, and we're passing in our task ID, which is specified in our parameters here. Remember that our subtask, when we want to create it, the client should be sending over a description. And only a description, aside from the task ID, which is specified in the params here. But we can just grab the body. So let's say body is json.loads, and then we have our request data, which is our request body. And then we can say our description is equal to body and then description, because this is going to be a Python dictionary. Now we're going to create our subtask using the information we're provided. Our ID is going to be, remember that in DB, we have our insert subtask. It's going to return an ID, which is the ID of the new subtask, which is what we're going to be using here. So we can have ID is our db.insert subtask. And then remember that takes in a description. By default, the done is going to be false, so we're going to pass in false. And now we're also going to pass in our task ID for our ID. So you can see here, VS Code is being nice, and it says, hey, we see that you're filling out your ID. Make sure that it is what you want it to be, which is our task ID. And then the rest of the fields, oops, we can just fill out from our body. So we know it's going to be description. We know our done is going to be false because that's what we passed in here. And then our task ID is going to be our task ID, which is specified up in our parameters. So this is going to, once we do that, since we call this function here, supposedly our database driver is going to go ahead and do that to our database. And then we can just return json.dumps, and then our response, which looks like success is true, and our data is going to be the subtask. So this is all good if, again, our task ID is a valid task ID that actually exists as a task. But what if that's not the case? Then we're going to go ahead and say that, oh, well, the success is true and here's our data, but that's not going to happen because within our database, it's going to throw an error. So we're going to have to try to catch that. So we can put all of this in a try block. And then if an error is thrown when this is called, so what's going to happen is that we call this function, it goes to db.py, and then here, when we execute this SQL statement, that's when the error is going to be thrown. It's going to propagate back up to our create subtask in app.py, and our error is going to be here. So we can go ahead and catch that. And this error is called SQLite 3, and it's called integrity error, which means like the integrity of your table is broken. So if this is the case, then we won't actually insert the subtask, which is good because we don't want that to be in our table. It's not going to be inserted, and we can just tell the client, hey, this didn't go through because you gave us an invalid task ID. So we can just return one of our error responses. What's our error? Task is not found. And we can give that a 404 code. All right, so we can also get, oh yeah, I'll give you some time to write that down. All right, so this route right here, get subtasks of tasks, this should return literally like just the subtasks. So it won't actually include any information about the original task. It'll just contain all the information about the subtasks of a task. This might be useful if you can imagine if you have an app, you have sort of like this nested task structure, and then you click on task, it'll like move to the next screen and it'll show you all your subtasks for that task. That might be useful. I don't know, I don't do front end. So this is very similar, again, to our get subtasks or get tasks because it's just going to return a list of subtask objects. So we'll have our response, looks like success, true, and the data is going to be the function we had where it's get subtasks of tasks or subtasks of task, and we're passing in our task ID here. And remember, we defined this in our db.py. Okay, and then we can just return json.dumps, our response, and 200. So looks exactly like get subtasks, but calling a different function for data. You can copy and paste. All right, finally, what if you want the task and all of its subtasks? So you don't want to just see the subtasks, you also want to know what the original, like, bigger task was. We can actually just go ahead and modify our previous getTask function. So we have here task equals getTask by ID, and then if the task exists, then we can just return the task. But now we also want to get all of its subtasks. So we already have a function for getting the subtasks of a task, remember? get subtask of task. So what we can do is modify our existing task object, which has everything except its subtasks, and say that it has a new field, subtasks, and we can just set that to our get subtasks of tasks, and then that's our task ID. So it's really easy to add data in this way, and you don't actually have to change any of your previous code to allow for this. So that's really nice, and this will also still handle the fact if like a task doesn't exist and like how are we going to get the subtasks. That's still in place from before. And remember, if we look at get subtasks of task back here, oh, why does this have an error? Invalid syntax. Hello? Is this fine? Oh.
Description.
Wow. What happened? Cool. Right. So remember that this will return an empty list if there are no subtasks, and that's exactly what we wanted. So we can just save that, and this should hypothetically all work. Let's do that. So let's open this up. Let's start up our server. Okay. Oh, near reference syntax error. Oh, it should be references, I believe. References, task ID. Just redo that. Cool. So our server is running. So to just show that these all work, I'm going to open up Postman. Let me make this bigger. Oh, very nice. All right. So let's first create a task so that we can have some subtasks. So we're just making a post request with our body, take a nap. Very important. So we can see here in our response body, we have a 201 created. And if we look at what's here, look, cool, we have our task. Now we can do create subtask. So our ID for our newly created task is 1. So when we create a subtask, we want to call this route, which is task 1, and then subtasks. And it's going to be a post request because we're making something new. And in our body, we have wash pillow sheets. You don't want to nap on a gross bed, I guess. So we can create that. And we can see our ID is 1 because, so IDs only have to be unique within a table. So this is ID 1 within the subtask table, while the ID in the task is ID 1 in the task table. And then we have our description, done, and then we can see here our task ID references 1, meaning the 1 in task. But what happens if we try to create a task for a subtask for a non-existent task? We can try doing it with task ID 0, and if we send it, we get our error response as expected. Cool. So let's create another subtask, I guess. We can do meditate. And let's just create that. Cool. So we have our meditation. Now if we, just as a sanity check, we can have our route that gets all subtasks. And this is a GET request. We send that, and we can see that it is successful, and it just returns a list of every single subtask. And we see that both of these subtasks refer to the same task. Finally, we can do what we set out to do, which is to get all the subtasks of one task. So we have task 1, our subtasks here. Oh wait, is that what I wanted? What's my route? Get all subtasks? No.
What was wrong with it?
I wanted to get the task. Oops, my bad. This is like literally the exact same thing as this route. I doubled up. All right, get task. So now, instead of just getting the task, we should return our task object with also its subtask. So we should be able to just send that. And we are returned our ID1, our take a nap, our done, and now we also have all of its subtasks, which is all this stuff. And you can see here that in here, I didn't include the task ID of each subtask because it's kind of self-explanatory if we're getting it by task. So that's just extra information. It's nice to not return everything that you kind of keep track of because a lot of the information the client is not going to need and it's just kind of a waste of like data. So just like feel free to filter out whatever that you feel like the client doesn't need or the client has told you that they don't need. Yeah, that's the demo. So
Should we talk about API spec for PA3?
Yeah, sure. So this is really small. There we go. Oh. You want to talk about it?
Yeah. All right, so the assignment for this week is actually not going to be due until Wednesday after fall break because none of us will be here. Well, none of the core staff will be here. Hopefully you aren't here as well. But that also means there are no office hours this weekend, and that's part of the reason why the assignment is due later next week. But I just want to go through the API spec for this assignment because some things are changing where we're actually starting to get into a new model for the transactions. So before, we never really had a model for a transaction. We would just manually update the balance, and then all that information is just represented in the user table. But now we want to actually keep track of each transaction that occurs in our database. So say we want to create a, here we go. So this is like kind of the model that we're trying to go for. So a transaction will keep track of its own ID, the timestamp for when the transaction occurred, along with the ID of both the sender of the money and the receiver, along with the amount, a funny little message with emojis if you're into that, and then this field accepted we'll get to for actually sending a request for payment versus manually like sending or receiving money. So the reason we have this accepted field is say we want to request something, we'd want to construct like a lot of the same information. So like when was the request sent, who do you want to receive money from, and like I want to receive money to my account, and like how much am I asking for. So what that looks like is the body for that would be all that same information, but accepted we want to set to null because the person on the other side has to either approve or disapprove the request. And that's the final route that we want you to implement, which is accepting or denying a payment request by either setting the accepted to true or setting it to false and then updating the information accordingly. So this is kind of like the gist we're going through. This is like makes the Venmo application a lot closer to what's actually really happening in Venmo when you send money to each other. So I just want to go through this API spec to give everyone some more context as to why we're doing what we're doing. But does anyone have any questions about what we're looking for, or otherwise, like, have a nice night. And we look forward to grading your homeworks, and we'll get the grades for PA2 done by Friday, hopefully. And best of luck with everything.